Hello and welcome to this video in which I will show you how to do bootstrapping in the Mplus software. My name is Geiser, I'm an instructor with QuantFish. So let's get started. First of all, when would you use bootstrapping at all? And so one application is when you have a confirmatory factor analysis or a structural equation model and you're interested in obtaining robust standard errors. Then one way to get robust standard errors, for example, because of non-normally distributed data, is to run bootstrapping and so get your standard errors and potentially also your confidence interval by bootstrapping rather than relying on, for example, asymptotic maximum likelihood standard errors. And so here I'm going to show you how to do that for a two-factor structural equation model, and then you can transfer that to more complex models as well. So you can see that here I have a model that is very simple with two factors, f1 and f2. f2 is predicted by factor f1, or f2 is regressed on factor f1, we could say, and each factor here has two indicators. And you can see that I added to my input file in Mplus the command analysis bootstrap equals 1000. And so that command prompts Mplus to get started on bootstrapping. So that already tells Mplus, okay, I'm supposed to do the bootstrapping and the standard errors for the parameter estimates are supposed to come from bootstrapping, not from regular maximum likelihood estimation. So your standard errors then will automatically be bootstrap standard errors. Now, what will not automatically be bootstrapped are the confidence intervals. So in order to get also confidence intervals based on bootstrap standard errors, you have to also include that bootstrap keyword in the output command in parentheses behind the confidence interval or C interval command. Otherwise, Mplus would still give you regular confidence intervals if you didn't include this command here, bootstrap in parentheses at the end. When you do that, then you can obtain asymmetric confidence intervals that are based on bootstrapping. And there are different options. So there is the regular bootstrap that is obtained with this keyword here. And then there's also bias corrected bootstrap in Mplus, which is then would be the keyword BC bootstrap. So if you put BC bootstrap instead of just bootstrap, then you get bias corrected bootstrapping. And that has an application, for example, in the context of statistical mediation analysis, where we test indirect variable effects. And those are often tested with asymmetric bias corrected bootstrap confidence intervals, because the product of two coefficients or more coefficients, meaning the indirect effect, is not normally distributed since it is the product of two or more regression coefficients. And so oftentimes we use asymmetric bias corrected bootstrap confidence intervals to test indirect effects. And I have a separate video on the bias corrected bootstrap for mediation models here on this channel that you can check out if you're more interested in how to do that and how to interpret that. So in this case here, I did regular bootstrap. So let's take a look at what the output looks like for a model like this. When we scroll down, you can see what is used for parameter estimation is regular maximum likelihood in this case. So it's maximum likelihood estimation still. It's only that the standard errors and confidence intervals now do not come from maximum likelihood estimation, but rather from bootstrapping. Now, bootstrapping also works with other estimators, and you can find the details in the Mplus users guide. When you go to the section in the users guide that talks about the analysis command, you can see for which estimators bootstrapping will work other than maximum likelihood. And we scroll down and it just all looks as usual. The fit statistics are regular fit statistics in this case. The p-value here for the chi-square is regular asymptotic p-value that is based on the chi-square distribution. Later I'll show you how you can also get a bootstrapped chi-square p-value for cases of non-normality. But here with the regular bootstrap, this is just the asymptotic p-value for our chi-square test of model fit. So this is not corrected for potential non-normality. Only the standard errors for the parameters are. And so you don't really see anything. It doesn't tell you those are Bootstrap standard errors. You would only see that if you compared those standard errors and test statistics to a run without the Bootstrap command, then you would see that there would be some differences here in those estimated standard errors. Also, when you go down, you have standardized model results, also with Bootstrap standard errors, and then at the end you have confidence intervals of model results that now are based on bootstrapping here. And so you find your estimate, the point estimate in the middle, and then the limits of different confidence intervals to the left and to the right of the estimate column. So lower 5% and upper 5%. Those two columns define the boundaries of a 90% confidence interval, lower 2.5% and upper 2.5%. Then those two define the limits of a 95% confidence interval. And on the far left and far right side, you have the limits of a 99% confidence interval. First for unstandardized parameter estimates, and then below that for standardized parameter estimates. And now these confidence intervals are also based on bootstrapping. Now there's another type of bootstrapping that is relevant for structural equation modeling when you have non-normal data, and that is the so-called Bollenstein bootstrap. And that is something that you can also get in Mplus, and then not only your standard errors will be bootstrapped, but also the p-value for your chi-square statistic. And that's relevant because with non-normal data, the chi-square fit statistic can also have a biased asymptotic p-value. So if you have non-normal data and you test your model and you use the theoretical chi-square distribution to find the p-value for the test statistic, then that can be biased or incorrect when you have non-normal data, and we can correct that with the so-called Bollenstein bootstrap. So how do you get that in Mplus? I have an example output file for that as well. So a two-factor SEM with Bollenstein bootstrap is obtained by putting the keyword residual behind the number of bootstrap samples. So again, here I'm specifying 1000 bootstrap draws, and then I put the keyword residual behind the 1000, and so then Mplus is prompted to run the Bollenstein bootstrap rather than the naive bootstrap that we did previously. And then again, you can include the bootstrap keyword in your confidence interval subcommand if you also would like to have those confidence intervals based on bootstrapping. Let's go down and see how that changes our output file. One thing that I forgot to show you earlier is that Mplus also will tell you whether all of the bootstrap draws were successfully completed. Here at the beginning of the output, you can see we requested 1000 bootstrap samples and also 1000 were completed, so that's a good thing. And when we scroll down, we see a slight modification in the model fit output, where now we not only get the asymptotic p-value for our chi-square test statistic, which we already saw previously was 0.6847, but we now also get the Bollenstein bootstrap p-value, which is very close to the asymptotic p-value in this case at 0.664. So the conclusion here would be no different. In either case, the model does not have to be rejected at the 0.05 significance level. So this model fits the data well. It's a simple model, has only 1 degree of freedom, so no wonder. But so in either case we would retain the model, but this may not always be the case. So sometimes the asymptotic p-value may be misleading if you have non-normal data, and then you would want to rely on the Bollenstein bootstrap p-value rather than this asymptotic p-value that is given here first. And then again, you get bootstrapped standard errors. Now these are different because they are obtained using the Bollenstein method rather than the naive bootstrap. So those standard errors here may be a little different than the ones that we obtained previously. And then once again, you also get your confidence intervals based on bootstrapping here as well. Now, those are the bootstrap options that Mplus has for maximum likelihood estimation and other estimators for structural equation modeling. There's another type of bootstrapping that you can do in Mplus that applies to latent class and latent profile analysis, and that's the bootstrap likelihood ratio difference test when you compare the number of classes in mixture modeling. For example, latent class analysis and latent profile analysis. And this is something that I show in a separate video on the bootstrap likelihood ratio test Tech 14 option in Mplus. So if you're interested in that type of bootstrap, then check out this other video as well. Thank you so much for joining me today for this video on how to do bootstrapping in Mplus, and I'll see you next time.